Now that we've discussed ionic bonding in the previous video, we can now talk about covalent bonding. Covalent bonding generally happens between a nonmetal and a nonmetal. And in this case, there is no transfer of electrons happening, so we don't have an ionic bond. And a covalent bond can be defined as the force that links nonmetals together in molecules. So in this case, atoms are held together by shared pairs of electrons. And this shared pair of electrons is called a covalent bond. And when they're held together by these shared pair of electrons, the two atoms collectively achieve the noble gas configuration. And typically, when we observe molecules that form covalent bonds, they have a very similar electronegativity, and that electronegativity is pretty high. So they really don't want to share the electrons, but they're willing to do so because that's the only way that they can achieve an octet. The most, or I guess the simplest case of covalent bonding happens in homogeneous diatomic molecules. So we'll look at 4 examples here, which are hydrogen gas, which is H2, fluorine gas, which is F2, oxygen gas, which is O2, and nitrogen gas, which is N2. So if we look at the hydrogen gas, we have 2 different hydrogens that need to form a bond together. And what they're going to do is they're going to have their orbitals overlap, so they share this pair of electrons right here. And typically, when we represent this shared pair of electrons, we use a dash to indicate that a bond is forming between these 2 hydrogen atoms. And this dash is going to be our shared pair of electrons. And in the case of hydrogen, we call this a single bond. For fluorine, these atoms act fairly similar to hydrogen, but in this case we have 7 valence electrons on each fluorine. So our Lewis structures indicate that we have 7 valence electrons on each fluorine, and they're going to form a covalent bond and share the 2 electrons that I've circled here. So when we draw a fluorine molecule, we have the bond forming between the electrons that I've circled, and each fluorine then has 3 lone pairs of electrons around it. So we have 1 shared pair of electrons, and then on each fluorine there are 3 lone pairs of electrons. And we represent each of these with a straight line. So that line is going to indicate a pair of electrons, and when we talk about bonding, typically we discuss it in terms of pairs of electrons. So now when we look at the oxygen molecule, we see a slightly different case. Each of these oxygens have 6 valence electrons. So we see something similar to the case that we did when we were looking at the ionic compounds. We have 6 oxygen electrons over here on the left that I've indicated with circles, and 6 on the right, which I've represented with squares. When this particular bond is formed, and when this orbital overlap occurs, the oxygen is sharing this electron over here. So we can count up our valence electrons now and say that we have 1, 2, 3, 4, 5, 6 from the oxygen on the right and 1 from the oxygen on the left for a total of 7. The right oxygen atom has 6 electrons I've represented with X's, and it's also sharing 1, which represents a circle. So right now, each of these oxygen atoms only has 7 electrons. So what has to happen is we need to form another covalent bond between the 2 oxygen atoms. So now when we count these up, we have 4 circles over here on the left, and then a circle and an X, and a circle and an X, giving a total of 8 electrons. So what happens is the oxygen molecule must form a double bond to achieve the octet. And we also have our lone pairs of electrons around the oxygen atoms. So our O2 molecule forms a double bond. With nitrogen, we have 5 valence electrons, and we can represent these based on our Lewis symbols. So when this nitrogen forms covalent bonds, it has, and let's analyze the nitrogen over on the left. There's 5 dots representing our valence electrons. If we form one covalent bond, it's going to share an electron on the right and give a total of 6. If we form another covalent bond, we're going to have now a total of 7 valence electrons, which means we have to form one more covalent bond to give us our 8 electrons. So the nitrogen molecule is going to have a triple bond to achieve the octet. And we also still have our lone pairs of electrons outside here. So one of the things that we can now do is look at and compare fluorine to oxygen to nitrogen. Okay, our triple bond over here is going to be the shortest bond length, and it's going to be the strongest, whereas our fluorine single bond over here is going to be the longest and the weakest. So a triple bond is going to be shorter and stronger than a double bond, which is shorter and stronger than a single bond. So this is what we can do, and how these molecules form our stable octet. And this is why they will exist as diatomic molecules rather than exist as hydrogen, fluorine, oxygen, or nitrogen atoms individually. So in order to form an octet, all the atoms are going to do anything they can. If that means forming single bonds, they'll do it. If they need to form double bonds, they can do that. And they can also form triple bonds. So in the next video, we'll look at something called bond polarity and use the periodic trend electronegativity to explain some of the properties of covalent bonds that will occur in molecules.